We present KnitKit, a flexible system for machine knitting of customizable textiles. CNC knitting machines are now capable of fabricating textiles with a wide range of shapes, textures, and materials. This, along with recent advances in fiber and yarn technologies, have created increasing potential for applications beyond the fashion industry. Functional properties such as electric conductivity and mechanical stiffness can now be embedded into the fabric via complex multi-yarn stitch patterns. Commercial CNC knitting machines are usually accompanied by a computer-aided manufacturing software that provides a visual interface for programming it. These interfaces allow the user to specify knitting instructions in terms of arrangements of stitch types or patterns. They require highly trained, skilled experts to painstakingly translate complex, high-level textile design into machine instructions. This puts a practical limit on the capabilities of these machines, as realizing complex textiles become a time-consuming and difficult task. In the past few years, several high-level design tools for the fabrication of knitted textiles has been developed. These methods are capable of automatically generating the machine knitting instructions from complex 3D models. The method proposed by Naranayan et al. Also allow for some low-level control by enabling the user to visually manipulate simple knitting primitives. While these works have certainly made the use of knitting machines more accessible, they focus on simplifying the geometry aspect of textile design and do not scale well for handling complex multi-material stitch patterns. For example, to knit an object with a rib pattern, the user has to manually specify alternating rails, and any tweaking to the design's geometry and scale would require the user to redo all the work. In this work, we aim to address this issue. Our objective is threefold. 1. To design a knitting system where the high-level geometric and fabric designs can be specified independently from the low-level instructions. 2. To be able to easily specify and configure complex multi-yarn stitch pattern. And 3. To retain low-level control over the instruction generation process in order to have a more flexible system. In summary, our system generates machine knitting instruction from an input design in two stages. At first, the system takes an input geometry and texture and builds the KnitNet data structure. This data structure encodes the topological information required to knit the input design. In the second stage, the system generates the required instructions from the KnitNet according to some user-defined rules and routines. The KnitNet allows us to make the high-level geometric and textile processing independent from the low-level aspect of machine knitting. In addition, the rules and routines allows our system to remain flexible, and the user can configure the scheduling process and extend the capability of the system in an independent manner. The KnitNet is a directional acyclic graph that captures the row-like structure of a knitted object. Its nodes correspond to the courses, and the connection between the nodes capture the wales. The direction attributed to the edges indicate the order in which the courses have been created. Each node of the KnitNet contains a list of stitches where information about the yarn material and stitch patterns are stored. Now, we describe how the KnitNet data structure is built from an input design. This input consists of a triangular mesh representing the knitted geometry and one or multiple 2D texture encoding the yarn and stitch pattern information. Our system also requires a vector field to be defined on the mesh that represent the intended knitting direction. Similar to the state-of-the-art methods, our high-level processing stage is based on a quad-dominant remeshing of the input geometry, where the vertices would correspond to the stitches of the knitted object. Therefore, we start by computing a 2D stripe parameterization using the method of Knopfeld et al. It ensures that the spacing between each stripe remains consistent. Then, we perform the remeshing by computing the intersection between two orthogonal stripes and connecting them. At this stage, we augment each vertex with the pattern and yarn information from the input textures. Finally, we cluster the vertices of the remeshed geometry along the horizontal stripes to get the nodes of the KnitNet and compute the connection between them using the input vector field. This will allow us to obtain the KnitNet. In the case where the input is a three-dimensional model, each vertex must be assigned to either the front or the back bed of the knitting machine. This means that the vertices of each node of the KnitNet must be divided into two groups, such as the boundary across successive nodes remain continuous. By setting the spacing parameter in NopAdAl's parameterization algorithm to the physical size of the stitch, we can calibrate our system to knit object of desired dimension and account for the changing size of the stitches along different patterns. In order to measure the size of a stitch in a particular stitch pattern, we first take a photograph of a knitted sample. Then, we blur the image in the horizontal and vertical direction to highlight the courses and the wale. We then compute the fast Fourier transform for each column and row and get the average distance between the courses and wales. Having built the KnitNet, we now use it to generate the knitting instructions. The biggest challenge in automating the generation of knitting instructions is dealing with its highly contextual nature. Even for simple actions such as knitting a single course, the low-level instructions depend on several factors. One, it can depend on the stitch type. For instance, the instruction to knit a single jersey course are totally different from the one required to knit a double jersey one. Two, it can depend on whether the yarn carrier is on the left or on the right. And three, it can depend on whether loops already exist on the needles, because if not, then some cast-on operation might be required. Before presenting our instruction generation algorithm, we introduce some terminology and concept. We define actions as abstract operation that a knitting machine can do. For example, a knit action would be the act of knitting a single course. A split action would be the act of splitting one branch into two. In order to keep track of the changes that are happening on the needle bed during the knitting operation, we encode this information with a state structure. In this structure, we store a list of contiguous needles containing one loop that we call islands, as well as the position of the last direction of the active yarn carriers. In this context, each action executed by the machine would change the state of the needle bed. For example, here, we can see that a split action divides the island into two and activates another yarn carrier. So, in order to generate the knitting instructions from the KnitNet, we proceed into two steps. First, we generate a list of actions according to some graph transformation rules. Then, we translate those abstract actions into actual operation by contextualizing them relative to the current state of the machine's needle bed, using some user-defined routines. The first step in this process starts by transforming the input KnitNet into an action graph. In order to build it, we start by dividing nodes of the KnitNet such that each one have a single incoming and outgoing edge. And then we compute its dual. While the KnitNet describes the structure of the knit object, its action graph represents the process of producing it. In this context, traversing the edge on the action graph corresponds to the act of producing the corresponding course. Therefore, the edges of the action graph would encode the actions. Having computed the action graph from the KnitNet and initialize its edges with simple knit actions, the goal now is to schedule them. We do that according to a double push-out graph rewriting algorithm that iteratively reduces the complexity of the graph while increasing the size of the action embedded into its edges. This graph transformation is done according to some rules that indicate how the actions are combined in a certain context. For instance, here are the set of rules required to generate the actions for the double torus example. Each rule consists of two graphs, a left one and a right one. The algorithm then would find a subgraph matching the left one and replace it with an instance of the right one. For example, here the make whole rule would replace the graph with two branches with a single linear one and add a split and merge action in the right place. The linear rule would remove one node from the graph and concatenate the actions and the edges. So, for this example, the algorithm proceeds as following. First, subgraphs corresponding to the left side of the rules are detected, and then replaced with the right side one. We continue this process until the canonical graph is reached. The edge here of the canonical graph would contain the list of actions that produce the input KnitNet. The goal now is to translate those abstract actions into low-level operations. To do so, we build a routine library where each action type is attached to several routines. Think of the routines as a small self-contained knitting program. In order to get the operations, we iteratively traverse the action list in the correct order. For each action, we first identify its type. Then, based on the information available from the node of the KnitNet, we select the appropriate routine. For instance, here it identified that we want to knit a single edge course. Then, using this information and the current state, we execute the routine. The result is the actual operation and the necessary information to update the state. The routine is where the operations are being generated according to the state that is given as input. The state is initialized by the actual configuration of the machine. It is important to note here that the rules and routine can be configured and extended by the user. Now we show some of the features of our pipeline. First, we show a simple rectangle consisting of various stitch patterns that each have very different size. We can tell that the size of each patch is consistent, and this is due to the geometric calibration that we did. Here also, we show another rectangle with two stitch types that were attributed using a texture. By only changing the texture information, we can see how the stitch pattern distribution is changed in the result. It is important to note here that the geometry was not changed, and none of the rules and the routines was either. Here, we demonstrate how we can knit colored textiles. So, from the image, we compute a dither luminance texture that we use to derive the knitting process. We then extend the knitting routines with a fair isle knit routine that can process the input from the texture and do the color work. A more complex example would take the CMYK values from the image and use that to drive the knitting. Here, all we have to do is to define the CMYK knit routine that would use these values to know which yarn to inlay. Again, to show how the instruction generation process is completely independent from the high-level design, here we show how the Fair Isle knit routine, the same one, can be used to knit a sphere with a map of the Earth. Here, we demonstrate how we can customize the scheduling. For instance, when doing a split, we can knit one entire side before moving on to knit the other one. The scheduling strategy would be problematic for big structures, as the user would have to deal with tension issues on the machine. Another way to schedule the split would be to alternate between knitting the right side and the left side. This comes at a cost of introducing floating yarn that would be cut later on. In our system, Swapping between both strategy is a matter of changing the split rule. The design or the lower level routines are not affected. Here, we show a colored hand model that was knitted using the alternating split strategy. To conclude, we presented KnitKit, a flexible and customizable knitting pipeline that allows us to assign stitch pattern and yarn material using textures. It also allows us to customize the knitting direction via a vector field and retain low-level control over the knitting process by modifying and expanding the action rules and routines. Thank you for your attention. You can scan this QR code to read the paper and have more information.